Something happened in the Chilean mountains that nobody fully prepared you for. A machine pointed its eye at the sky, and in its very first glance, it didn't just find stars. It found secrets that had been hiding in plain sight for millions of years. Secrets that rewrite what we thought we knew about galaxies, about asteroids, about the architecture of our entire solar neighborhood. And here is the part that should terrify you just a little. This telescope hasn't even fully started yet. What you are about to hear is not a preview. This is what happened when humanity's most powerful eye opened for the very first time. There's a mountain in Chile called Cerro Pachón. It rises 2,182 meters above sea level, carved by geological time into a plateau so high and so dry that the air itself becomes a scientific instrument. The atmosphere up there is thin, clean, and transparent, nearly free of the moisture and pollution that blinds every other telescope on Earth. For decades, astronomers dreamed about placing something extraordinary on that peak, something so powerful it could change not just what we see, but what we understand about the universe we live in. That dream has a name, the Vera C. Rubin Observatory, and what it has already done, before its main mission even officially began, has shaken the scientific community to its foundations. Think about that for a moment. Not during its 10-year survey, not after years of data collection, before any of that, in its first glances, in its opening hours of operation. What this machine has already revealed is something that decades of astronomy, thousands of scientists, and hundreds of millions of dollars in prior telescope investment completely missed. And the question you should be asking right now is not what did it find? The question you should be asking is, if this is what it found while warming up, what is it going to find when it actually gets started? To understand why this matters, you first have to understand what the Vera Rubin Observatory actually is, because most people who have heard the name have no idea what they are dealing with. This is not a telescope in any ordinary sense. The camera sitting inside this observatory is the largest digital camera ever built for astronomy in the history of human civilization, 3.2 gigapixels. To put that in perspective, the average smartphone camera you're holding in your hand right now operates at roughly 12 to 50 megapixels. The Rubin camera is over 60 times more powerful than that, and it is pointed not at someone's dinner plate, but at the entire visible southern sky. Every single night, every few nights, it completes a full sweep of 18,000 square degrees of sky. And it will do this every 3 to 4 nights, without stopping, for 10 consecutive years. But here's where it gets complicated, in a way nobody is explaining clearly enough. The observatory was named after Vera Rubin, a woman whose scientific legacy is embedded in its very DNA. Vera Rubin was the astronomer who, in the 20th century, gave us the first truly convincing evidence that dark matter exists. She did it by studying how galaxies rotate, and discovering that the stars on the outer edges of galaxies moved far too fast for the visible mass of those galaxies to explain. Something invisible was holding them together, something that made up the majority of the mass of the universe itself. That's something we now call dark matter. And the observatory bearing her name was built at its core to chase that mystery further than any instrument before it ever could. Before it was named in her honor, the project had a simpler, more direct name. It was called the Dark Matter Telescope. Read that again. The machine that is right now staring into the sky above Chile was originally conceived as humanity's primary weapon against the greatest unsolved mystery in all of physics. Dark matter makes up approximately 27% of the universe. Dark energy makes up another 68%. Everything else, every star, every planet, every galaxy, every living creature, every atom of every substance science has ever studied, makes up 5% of what actually exists. 5%. And the Rubin Observatory was designed to investigate the other 95. That context matters enormously, because what it has already found was not what anyone was looking for. Not yet. What it found came as a surprise, and in science, surprises of this magnitude tend to rewrite the books. The first major discovery came in June of 2025. The observatory had not yet begun its legacy survey. It was still in its commissioning phase, still being tuned and calibrated, still being checked and rechecked by engineers and scientists. In this phase, the telescope captured what were called the Virgo First Look images, a set of trial images pointed at the Virgo cluster, the largest and most thoroughly studied cluster of galaxies in the known universe. Astronomers have been looking at the Virgo cluster for over a century. Every major telescope in history has pointed at it. It has been mapped, measured, photographed, and analyzed thousands of times. There was nothing new to find there, or so everyone thought. Buried in those first look images, in what was supposed to be a routine calibration target, astronomers spotted something that had never been seen before. Extending northward from the spiral galaxy Messier 61, a galaxy so well known it has its own catalog entry, so thoroughly studied it has its own Wikipedia page, so photographed that it has appeared in textbooks for decades. There was a structure, a long, razor-thin stream of stars, stretching for approximately 163,000 light-years. That is longer than the entire visible diameter of our own Milky Way galaxy, which spans roughly 100,000 light-years across. This stream, wider than 10,000 light-years at its broadest point, had been completely invisible to every instrument that came before. The Virgo cluster had been a closed book. Rubin opened it and found a hidden chapter written in starlight. What most people are not seeing is the full weight of what this implies. Messier 61 is not a distant, obscure target. It is one of the largest spiral galaxies in the Virgo cluster and sits approximately 54 million light-years from Earth. 54 million light-years is, in cosmic terms, relatively close. Close enough that we should have seen everything worth seeing long ago. The fact that this stellar stream remained hidden until now is not just a discovery about Messier 61. It is a statement about the limitations of everything we built before Rubin. Every telescope, every survey, every cosmic map. All of them were looking at the universe through a keyhole. The Rubin Observatory just kicked the door open. The research paper that formally announced the discovery was led by Aaron Romanowski of San Jose State University and published in the research notes of the American Astronomical Society. The paper stated what the data made unavoidably clear. The stream is almost certainly the remnant of a dwarf galaxy that was torn apart by Messier 61's gravity over a timescale measured in billions of years. A whole galaxy, consumed and stretched into a river of stars, slowly wrapped around its killer like a scarf of light. And more than that, the interaction between this dwarf galaxy and Messier 61 may have triggered the starburst activity and galactic bar formation that define M61 as we see it today. In other words, the secret history of a galaxy's birth was hidden in plain sight, completely undetected for the entire history of modern astronomy, visible only to an eye powerful enough to see it. Because while the stellar stream revelation was still being processed by the astronomical community, the Rubin Observatory turned its attention to our own solar system. And what it found there set a completely different kind of record. In just 10 hours of observation time, spread across 7 nights between April and May of 2025, the Rubin Observatory identified more than 2,000 previously unknown asteroids, 2,104 to be precise, in 10 hours. For comparison, all ground-based and space-based observatories combined discover approximately 20,000 asteroids in an entire year. Rubin achieved roughly 10% of the entire global annual asteroid. Discovery rate in less than half a day. When its full 10-year legacy survey begins, projections from the observatory's own team suggest it will discover millions of new asteroids within the first 2 years alone. Millions. The solar system map humanity has been building for centuries is about to be completely redrawn, and here is where the story takes a turn that scientists are still trying to fully explain. Among those thousands of new asteroids, a team led by University of Washington astronomer Sarah Greenstreet found something that violated everything we thought we understood about how large asteroids behave. They found an asteroid that should not be able to exist, at least not in the form it takes. The asteroid is catalogued as 2025 MN45. It sits in the main asteroid belt, the ring of rocky debris orbiting between Mars and Jupiter. It is approximately 710 meters in diameter, roughly 2,300 feet wide, taller than most skyscrapers on the surface of the Earth. It is enormous. At that size, it should behave in a certain way, governed by physics and gravity and the mechanical properties of rock and metal. But 2025 MN45 does not follow those expectations. It spins, not slowly, the way large asteroids are supposed to spin. It completes one full rotation every 1.88 minutes, one full rotation, in less than 2 minutes. For a rock nearly 3/4 of a kilometer across, the spin rate is so extreme it breaks every previous record for an object in its size class. It is now officially the fastest spinning asteroid, larger than 500 meters, ever discovered by science. Think about what that means. At that rotation speed, the surface of 2025 MN45 is experiencing centrifugal forces that should, by conventional understanding, tear the asteroid apart. Most large asteroids are not single solid rocks. They are rubble piles, loose collections of material held together by gravity and weak internal cohesion. At the spin rate of 2025 MN45, a rubble pile would fly apart in seconds. The fact that it holds together suggests its internal structure may be fundamentally different from anything we have cataloged before. It might be a monolith, a single coherent mass of dense material. Or it might represent a composition and structural bonding we do not yet have a framework to fully explain. Either answer is scientifically extraordinary. Either answer demands follow-up. Either answer rewrites our model of asteroid formation and evolution. But 2025 MN45 was not alone. That is the part that most coverage is missing entirely. Along with that record breaker, Rubin's data revealed 18 additional super-fast and ultra-fast rotating asteroids, 19 total, all discovered in the same data set, all from the same 10 hours of observation. 16 of them were classified as super-fast rotators, completing full rotations in anywhere from 13 minutes to just over 2 hours. 2 additional asteroids were classified as ultra-fast, spinning in under 2 minutes, placing them in the same extreme category as 2025 MN45. All of these objects were larger than 90 meters in diameter. All of them live primarily in the main belt, and almost none of them would have been detectable by any instrument that existed before Rubin came online. What this represents is not just a set of interesting discoveries, it is the first glimpse of an entirely hidden population of objects in our own solar neighborhood that nobody knew was there. Objects close enough, in cosmic terms, to study in detail. Objects whose existence challenges the models that planetary scientists have used to describe the solar system for generations. The question is no longer whether those models need updating. The question is how dramatically and in what direction. According to informed sources within the astronomy community, what makes this particularly significant is not just the spin rates themselves. It is what the spin rates imply about the collision history of the asteroid belt. Fast rotators are thought to form through specific types of high-velocity collisions between larger parent bodies. Finding many of them in this concentration suggests either that the asteroid belt experienced a more violent and complex early history than current models account for, or that our previous surveys were simply blind to an entire class of object that has always been present. Both possibilities have enormous implications for our understanding of how the solar system formed, how planets grow, and ultimately how Earth itself came to be. And then, extending even further out, the observatory found something even more distant and strange. In that same data set, Rubin identified 380 trans-Neptunian objects, bodies of ice and rock orbiting beyond Neptune, in the outermost, coldest, most poorly mapped region of our solar system. Among them were 2 objects, designated 2025 LS2 and 2025 MX348, located at distances approximately 1,000 times greater than the distance between Earth and the Sun. 1,000 astronomical units. To give that scale meaning, the distance from the Earth to the Sun is approximately 93 million miles. These 2 objects orbit at distances of over 93 billion miles from the Sun. They are so remote that even sunlight, traveling at 186,000 miles per second, would take over 8 hours to reach them. They sit in a region of space so dark, so cold, and so distant that the possibility of detecting them at all was considered essentially beyond reach before Rubin existed, and yet there they are. The real story is that we are not dealing with incremental progress here. We are dealing with a phase transition in human knowledge. The kind of shift that happens maybe once in a generation, maybe once in a century. Every previous instrument gave us a partial map, a rough sketch drawn in broad strokes by tools that were doing the best they could with what they had. The Vera Rubin Observatory is not drawing a sketch. It is rendering a photograph, high resolution, full color, time-stamped, and updated every few nights. And even before the main survey began, before the machine was technically ready to do its full job, it had already fundamentally changed the picture. By July of 2026, the legacy survey of space and time officially began. The decision to start was made after a period of careful review that examined image quality, data system performance, survey speed, system reliability, and calibration accuracy. The start was delayed slightly from initial projections because the team refused to launch until the system was operating at its highest possible standard. And when it finally did launch, it did so with a camera already proven in combat. A camera that had already shattered records. A camera that had already found things nobody was looking for. But here's where it gets worse, or rather bigger, depending on your perspective. The actual science targets of the legacy survey go far beyond asteroids and stellar streams. The primary mission of the 10-year survey is to investigate the nature of dark energy, the force that is causing the universe to expand at an accelerating rate. This acceleration is one of the most disturbing facts in all of physics. The universe should be slowing down. Gravity should be pulling everything back together. Instead, everything is flying apart faster and faster. Something is driving that expansion. Something science has named dark energy, but is never directly detected, never directly measured, and never directly explained. The Rubin Observatory will attempt to constrain what dark energy actually is by observing the distorted light of billions of distant galaxies, a technique called weak gravitational lensing, where the mass of everything between us and a distant galaxy bends that galaxy's light in subtle, measurable ways. By mapping those distortions across billions of sources, Rubin will build the most precise picture of how mass is distributed across the universe that science has ever attempted. And from that picture, it will try to decode the nature of the force reshaping space-time itself. What most people are not seeing is the scale of what that undertaking means in practice. In the first few years of LSST data alone, the observatory is expected to send out millions of automated alerts every single night. Real-time notifications of anything that changed in the sky since the last observation of that patch. Every transient event, every supernova, every asteroid that moved, every variable star that fluctuated, every object that appeared or disappeared. Millions of alerts per night being processed automatically and distributed instantly to astronomers around the world. The sheer volume of discovery that is about to pour out of this system has no precedent in the history of science. The commissioning data alone, the test data, the warm-up data, the data that was never supposed to make headlines, produced the first peer-reviewed scientific paper using images from the LSST camera. That paper, detailing the discovery of 2025 MN45 and its fellow fast rotators, was published in January of 2026. It was the first of what will almost certainly become thousands. The commissioning phase also produced 11,000 previously unknown asteroids in total, confirmed entirely new objects that had never appeared in any catalog, never been photographed, never been tracked. 80,000 additional known asteroids were also detected, essentially confirming the accuracy and precision of the instrument, and 380 trans-Neptunian objects, all before the main survey launched. According to informed sources in the planetary science community, the implications extend well beyond academic classification. The detection capability of Rubin means it will be the most effective observatory on Earth for identifying near-Earth asteroids, objects whose orbits bring them into the neighborhood of our own planet. In the June 2025 first look alone, 7 near-Earth asteroids were discovered, all confirmed to pose no immediate danger. But the systems Rubin has in place to detect such objects are operating at a sensitivity no prior instrument could match. For the first time in history, humanity has a tool capable of building a genuinely comprehensive inventory of potential impactors. Objects that could, on timescales ranging from decades to centuries, represent a real threat to Earth. This is not science fiction. This is planetary defense infrastructure being quietly assembled in the mountains of Chile, one nightly scan at a time. And the stellar stream discovery carries its own separate weight of consequence. The paper's authors wrote something that stopped scientists cold when it was published. They noted that it was remarkable, their word remarkable, that a structure of this scale around a galaxy as well known as Messier 61 had gone entirely undetected for the full history of modern telescopy. And then they said something that may be the most important sentence in any astronomical paper published in 2025. They said, "We expect a treasure trove of substructures to be unveiled around other galaxies with future Rubin data." A treasure trove. Think about what those words mean, coming from scientists who are being conservative by professional obligation. If the first image, the trial image, the calibration target, the practice run, revealed a stellar stream 163,000 light-years long that nobody had ever seen, despite decades of looking, what is waiting in every other galaxy that has ever been studied? What hidden structures surround every spiral, every elliptical, every irregular galaxy that has appeared in every catalog ever compiled? How many ghost galaxies, devoured, stretched, reduced to rivers of dim starlight, are wrapped around the systems we thought we fully understood? How wrong was the map? The answer, if the stellar stream around Messier 61 is any indication, is very wrong in very interesting ways. What makes the Rubin Observatory uniquely capable of answering these questions is a combination of factors that no prior instrument possessed simultaneously. First, its camera. The 3.2 gigapixel LSST cam, built at SLAC National Accelerator Laboratory, is not just large. It is extraordinarily sensitive to objects with very low surface brightness, objects so dim that they produce barely any detectable light against the background of the sky. The stellar stream around Messier 61 was detected at a surface brightness of roughly 28 magnitudes per square arc second in the G-band. That is extraordinarily faint. Previous surveys could push to about 28.5 magnitudes with great effort. Rubin's full 10-year survey is projected to reach 30 to 31 magnitudes per square arc second across the entire southern sky. That is more than 3 magnitudes deeper. Each magnitude corresponds to roughly 2.5 times the brightness sensitivity. 3 magnitudes deeper means detecting things approximately 15 times fainter than what the best prior surveys could capture. 15 times in every direction the telescope points. Second, the cadence. Rubin will return to the same patch of sky hundreds of times over its decade of operation. This is not just about depth, it is about time. By revisiting the same locations over and over, Rubin builds not just a map of the universe, but a movie. Changes become visible, motions become trackable, objects that were invisible in a single exposure reveal themselves across multiple passes. Dark matter distributions, traced by the slow ballet of millions of galaxies, become statistically measurable. The universe, rather than being a static painting viewed once, becomes a dynamic system observed continuously. What was hidden behind stillness is now exposed by motion. Third, the data system. Every alert generated by Rubin is processed and distributed in near real time. Scientists anywhere in the world can receive a notification within 60 seconds of the observatory detecting something new. The infrastructure is built to handle millions of such alerts per night indefinitely. The scientific community is not waiting for data releases scheduled months or years apart. They are standing next to a live fire hose, receiving a continuous stream of the universe's secrets as fast as the telescope can generate them. Now add those three capabilities together. Deepest sensitivity ever achieved, highest cadence ever maintained, fastest data distribution ever built, pointed at a sky that has already proven, in its very first images, to be hiding things nobody expected. And ask yourself what 10 years of that is going to produce. The answer, according to every projection in the scientific literature, is a complete transformation of astronomy. Not an update, not a refinement, a transformation. The kind of shift that happened when Galileo first pointed a glass at the sky and found moons orbiting Jupiter. The kind of shift that happened when Edwin Hubble proved that the fuzzy patches in the night sky were not clouds within our galaxy, but entire separate galaxies beyond it. The Vera C Rubin Observatory is the next instrument of that magnitude, and it is already delivering. What the mainstream coverage has consistently failed to communicate is the cumulative weight of what we are talking about. Each individual discovery, the stellar stream, the record-setting asteroid, the superfast rotators, the 11,000 new objects, the 380 trans-Neptunian bodies, is extraordinary on its own terms. But together, they are telling a coherent story, and the story is this. The universe is dramatically more complex, more detailed, and more full of surprises than any instrument built before Rubin was capable of revealing. Our map was wrong, not slightly wrong, fundamentally wrong, full of blank spaces that we mistook for empty ones. And now something is filling those spaces in, night after night, scan after scan, alert after alert. A machine on a mountain in Chile is systematically dismantling the boundaries of the known universe and replacing them with something stranger, richer, and far more interesting. The LSST has officially started. Real-time alerts began flowing from the system in February of 2026. By the time you read this, the observatory has already completed hundreds of hours of survey mode observations. The data is accumulating, the papers are being written, the discoveries are being processed. Some of them will reach the public in weeks, some will take months, some will take years to fully understand. But what the commissioning phase has already proven beyond any reasonable doubt is that Rubin will deliver, not because of what was promised on paper, but because of what it already put on the table before anyone asked it to, which raises the question that no one in the mainstream conversation is asking loudly enough. If 11,000 unknown asteroids, one galaxy-spanning stellar stream, one impossibly fast-spinning rock, and hundreds of the solar system's most distant objects can be found in the warm-up data alone, what exactly is already in the main? Survey data that has not yet been analyzed? What is sitting in the servers right now, waiting to be processed by an algorithm or noticed by a human eye? What rewrite of our understanding of the solar system, the galaxy, the dark universe, or the laws of physics themselves is already in the buffer, already captured, already waiting? We do not know. Nobody does. And that is the most important sentence in this entire story. The universe has been keeping secrets from us for the entire history of modern science, not because the secrets were not there, not because the physics was impenetrable, but because we were looking at the sky through instruments too weak to see what was actually present. The Vera C Rubin Observatory has changed that. Permanently, irreversibly, and we are only at the very beginning. The first chapter has been written. It contains a galaxy's hidden past, a solar system more populated and more violent than we imagined, and a rock spinning so fast it should not exist. What does the second chapter hold? What is the third? What comes after 10 years of the deepest, most comprehensive survey of the universe ever attempted by any civilization on this planet? Nobody knows. Not the astronomers, not the engineers, not the data scientists, not the institutions that funded it. They can model probabilities and make projections and run simulations. But the actual content of what is coming, the specific discoveries, the precise rewrites, the exact moments when something in the data breaks an assumption everyone held to be unbreakable, that is unknown. And that uncertainty is not a limitation. That uncertainty is the point. That uncertainty is what makes this the most consequential scientific instrument operating on Earth right now, not because of what it has found, but because of what it has not found yet, and what it absolutely will. Something is coming out of that data, something big, possibly several somethings, and the only guarantee is that when it arrives, it will look nothing like what anyone expected. The mountain keeps watching, the camera keeps clicking, the universe keeps revealing, And none of us, not one person alive today, knows what it is about to show us next.